Welcome to lecture number 6 in New N302. Last lecture we discussed different conditions that we need to meet in order for reactions to occur. We've been talking about the Q value of a reaction for the last few lectures. In the most recent lecture we discussed additional barriers that we need to be mindful of and overcome in the event that we want the reaction to be able to occur. We talked about the Coulomb barrier, and that's going to be applicable when we have a positively charged projectile. The nucleus is always going to be positively charged, and so when we have those two charges, like charges, there's some additional barrier that we have to overcome. We talked about the threshold barrier, which is going to be applicable when we have a negative Q value. And so we discussed these different scenarios where all with the intent of trying to understand whether the reaction can occur or not. And so today we're going to continue talking about that, but we're going to discuss what's known as the center of mass or the center of momentum frame of reference. So up until now, we've always considered our frame of reference to be tied to the target particle, so the large mass particle on the reactant side of the equation. And today we're going to discuss an additional frame of reference that can be useful in some situations. We will go back and forth, and throughout the entire semester we'll probably spend the most time on what's known as the lab frame of reference, which is what we're used to doing up until this lecture. But it is of value to be aware and know when and how to use what's called the center of mass frame of reference. So that's going to be the focus of today's lecture. In order to set the stage, though, we're just going to jump into the first example, which doesn't really have anything to do with the center of mass frame of reference, but it's like I said, it's going to set the stage for us. So in this first example, we're looking at spontaneous decay, and in this case, it's going to be an alpha decay of uranium-238. And so we want to know the Q value. We've calculated this before. We can do it again, and we want to know the net momentum before and after the decay event. And that's really the extra piece that is going to help set the stage for our discussion today. And so for a spontaneous decay of any kind, we don't have a projectile. Right? So that the lowercase x, the mass is 0 because we don't have a projectile. Before the event occurs, we just have one large mass nucleus. And so that's what's unique about this situation, is that there is spontaneous decay. What that means is that there is no projectile on the reactant side. And so what does this look like? If we wanted to write the notation of a reaction, we've got U-238. And normally in this first entry inside the parentheses, we're going to put the reactant, so we're just going to either leave it blank or just write 0 there. But we've got the alpha particle that's being ejected as part of this spontaneous decay. And we're going to become some new isotope and new element. And so the alpha particle is going to have 2 protons and 2 neutrons. And so I have a total of 4 nucleons that are now no longer in the nucleus that I just had. So this is going to be 234. And because I've lost 2 protons, I'm going to go from a mass number of an element of uranium, which has 92 protons, to something that has 2 less than that, which would be thorium. And so if I wanted to be complete here, I'd write a 92 and a 90. So that's my reaction. I basically have a large mass here, and my alpha particle is going to be ejected. Let's say I've got 2 neutrons, 2 protons. It's ejected at some angle here. And since I didn't have a projectile, then this entire remaining nucleus, so this thorium-234 nucleus, is going to be going to gain some momentum in the exact opposite direction as whatever the alpha particle is ejected at. And so the momentum here, the momentum vectors and the velocity vectors are in opposite directions. And so what that does, and so let's write the expressions here. We have the mass of our projectile is 0. The mass of our U-238 which is our target. We can look this up in any chart of nuclides, any kind of AMU table. You have data that's given to you. You should be creating functions and scripts that take inputs of number of neutrons, number of protons, number of nucleons, and then gives you the AMU value. And so if we look this up, it's going to be 238.050788 AMU. And on the product side, we've got our alpha particle, which again we looked this up with the AMU table or chart. And we likewise look up the mass for our heavy product, which is going to be our thorium-234. 234.043601. So we've got these masses. We can easily find the Q value. The Q value is going to be 4.2698 MeV. And because this is a positive value, then what we have here is a spontaneous decay. In other words, we've just verified that it is indeed a spontaneous decay. The Q value informs us of that. And so I don't need to calculate the Coulomb barrier. I don't need to calculate the threshold barrier because I don't have a projectile in this case. And so my Q value, the fact that it's positive, I've got spontaneous reaction there, which in this case is a decay. And again, I can go double check this. Once I create my Q value analysis script or calculator, then I'm home free. But I can always check just to make sure and verify that my calculator is doing things correctly. So this is the Brookhaven National Lab. We showed this before, but if we look at the Q value calculator here, then I want to use a decay, and my parent here is going to be my 238 uranium. The decay mode is going to be alpha, and then I hit submit. And so just like we discussed, we're going from U-238 down to thorium-234. This is an alpha decay, and this gives me my Q value for that reaction. And so this is 4269.9 keV or 4.27 MeV, which is what we had calculated. So now going back to the problem, we've got the Q value, and what we want to do now is calculate the net momentum before and after this event. So if we talk about before, we have the frame of reference is on the U-238. That's where we're tying our origin to. So now that we're on this, not 283, 238. So with our origin on that nucleus, then the velocity of that nucleus is going to be 0. And so the momentum of that large particle is also going to be 0. If I have no velocity, I have no momentum. And since we've already talked about there being no projectile because it's a spontaneous decay event, then my mass of projectile is obviously 0, which also means that my momentum of that projectile has to be 0. I have no mass, I have no velocity, I have no momentum. And so this is an easy one. my net momentum before is going to be 0. Now let's talk about after. So after the event, if I look at the momentum, my momentum is going to be mass times velocity. And I know that velocity, if I relate that to kinetic energy, because most of the times we're talking about things in MeV, and that's in reference to our kinetic energy. So kinetic energy is 1/2 mv squared. So I solve for v in that case, I get 2 times the kinetic energy divided by the mass square root. And so my momentum is just going to be 2 times the mass times the kinetic energy square root. And from the previous lecture, from lecture 4, when we had no projectile kinetic energy. So in this case, we don't have a projectile, but we also don't have projectile kinetic energy. But even if we had a projectile with no kinetic energy, we'd be able to state the following. That our kinetic energy of the light product is going to be the mass of my heavy divided by the sum of my masses from the products times the Q value. And likewise, my kinetic energy of the heavy product is just going to be same denominator, different numerator times Q. And so what does that mean in terms of momentum? That's my kinetic energy. My momentum is going to be 2 times the mass. So my momentum of the heavy particle on the product side of the reaction is going to be 2 times the mass of that particle multiplied by the kinetic energy, which we just solved an expression for. So that'll be equal to, let's see, so m y over my plus my. There's Q, and then I've got to take the entire quantity of that and the square root of that. So that's my expression for the momentum of the large particle. My momentum of the light particle is similarly going to be 2 times the mass of that particle times its kinetic energy, which is mass capital Y over the sum of my masses multiplied by Q. And so you can see that these two here are equal in magnitude. And because they're equal in magnitude and we know they're opposing, in their direction, then I know that my net momentum in this case is also 0. So before and after this event, my net momentum is 0. So why did we go through that? And it might have been straightforward that was the case, just intuitively. If I have the alpha particle eject one way, the recoiling nucleus has to be sent the other way, directly opposing. But the momentum also has to be equal, because I didn't have any other momentum before this event. Everything was just post the decay, post the ejection of that alpha particle. So we did this to help us understand what this whole center of mass frame of reference is in reference to. So let's start with this binary reaction now, where we've got light particle, our projectile, and that's going to be sent to the heavy particle, our target. And then we're going to get some sort of heavy particle over here and light particle over here. And this ejection angle, emission or ejection, that's normally phi here. This angle is phi, and this one is theta. What we did up until this lecture is we're putting our frame of reference on this target particle. So this here is our frame of reference. And we're going to call this the lab frame. So we used this in the lab frame, which we're going to use the variable capital L. And so because we tied that to our lab frame, then our kinetic energy of the large particle, so our target, is going to be 0, because that is our frame of reference. If it happens to be moving, well, our frame of reference is moving as well. And therefore, my momentum vector is also going to be 0. So in general, though, we have info about the reactants, so we know the kinetic energy, momentum, and we want to know quantities tied to the product. And so the question is, what frame of reference choice enables this to take place most easily? And the answer to that is what's called my center of mass reference frame. And we're going to use a capital C for that. And this is also called center of momentum. And so rather than have the reference frame be tied to the target, we're also not going to have it tied to the projectile, but we're going to have it somewhere in between those two. And so if I'm sitting here, we're going to call this VC. If I let my reference frame not be tied to either of these, and I have it be translating at some velocity, then if I'm sitting on that reference frame, I'm sitting at its origin, then the projectile, if my velocity is less than the projectile velocity, let's say, then if I look backwards, then it looks like the projectile is coming towards me, and if I look in front of me, it looks like the target's coming towards me. And so this reference frame has both the target and the projectile coming together and colliding at the reference frame, basically. And so we want to choose some velocity. We could choose any velocity we want to, but we want to choose a velocity, this VC, such that before the reaction I have a net momentum of 0, just like we saw for the reactant side after the reaction on that example 6.1. And I also want to achieve that same condition on for the net momentum after the fact. And what this does for me is allows me to say that, okay, if I know the ejection angle here, I know that the ejection angle for the light particle, then the ejection angle for the heavy particle is just going to be exactly opposite that. And this table that we see here, this is the basis for this whole center of mass or center of momentum reference choice. And what the velocities and the energies we're dealing with are very far from relativistic, and so there's not going to be a difference between those two. And so if I use center of mass frame sometimes and I use center of momentum frame other times, don't be confused. For what we're doing in this course, those are one and the same. And the fact that we're looking for something that has a net momentum of 0 both before and after, that again is the basis for this center of mass center reference frame. And so for me, it's easiest to visualize on the reactant side, just like we had illustrated up here with some vector. And so if I choose this carefully, it's going to look as if the projectile and the target are coming towards me and colliding and then recoiling from that collision, both of them. And if I look at the momentum on this one, the momentum of that one, then they cancel each other out, and that's what I'm looking for. I want to choose VC such that happens. So we'll start with the lab reference frame, and we've got the expressions here, I've got momentum of the target and momentum of the projectile. So this is my total momentum before the interaction. And now we're going to introduce this velocity, Vc, relative to the, we want to introduce this relative to the lab frame of reference. And so what we're going to see is that we have mx times this Vx minus Vc. It's the relative velocity now since I'm in a different frame of reference. Plus the same thing for my target. Now, for everything we've done so far, this quantity here, we've assumed that to be 0, but we can still assume that, and we will go back to that later on in the lecture. But for now, let's even make this more generalized and have that be non-zero. So then we got Vx minus Vc there, and in order to make this eventually be equal to the frame of reference in the lab, which is just mx Vx plus capital X, then we're going to have to add the following. And this now is exactly true on both sides. And so I can literally choose anything I want to for Vc and have the left side of this equation be equal to the right side of the equation. And the idea is to choose a Vc such that these first two terms, which is the total momentum now in my new frame of reference, I want that to be equal to 0. That's the whole basis for this. And so I take this, and I want these two terms to add to 0. I'm going to choose it such that these two terms are 0. And if they're going to cancel out, then I can just solve for that Vc. I can set these two terms equal to 0, solve for Vc, and once I do, then I'm left with x times Vx minus Vc plus capital X Vx minus Vc equals 0. That's going to give me an expression for Vc, and that's going to be mx Vx plus mx Vx divided by the sum of my masses. So if I choose now that reference frame to have a velocity equal to this expression, then when those two collide, the net momentum approaching that collision is going to be 0. And I can do the same thing on the product side of the equation. And that's one thing that people get confused about in this analysis, is the fact that I am allowing, and by virtue of energy mass conservation, I need to allow for a different velocity after the reaction occurs. The scenario is the same in that I'm trying to get the net momentum to be 0 in both the reactant side and the product side. But the value of that velocity that I need to use in order for that to happen is going to be different for each of those. And so I have Vc equal to this expression here, and then we will call this Vc prime to denote the velocity that we need to achieve after the reaction. And so this one will be my. We could do the same thing and set the first two terms equal to 0 for the product side. And we'll get the following over the sum of the masses there. Oh, I forgot a parameter here. We have to Oh no, I didn't. No, that's right. Okay, so the numerators of these two expressions, I've got my velocity before the interaction and the velocity after the interaction. So the numerators of these have to be equal. That is my conservation of momentum. I've got the momentum, my total momentum before the interaction and my total momentum after the interaction. Those two need to be equal. And so because of that, I can say, is this numerator and that numerator, momentum conservation, we'll say, before and after the collision. So that means that I could also express this VC prime as a function of VC. So this will end up being mx plus mx over my plus my. So if I know the velocity of my center of mass reference frame before, I can use this to calculate what velocity of that reference frame I need to have after, such that both before and after I have a net momentum of 0. And so that's, again, what we're after here. And you notice this quantity down here, this quantity that I'm highlighting here, that is going to be equal to a unity. It's going to be equal to 1 when Q equals 0. And Q equals 0, if you remember, this is a scattering reaction. And so if I have a neutron coming in, a neutron coming out, I'm not changing the isotopic nature of the reactant. And so this is just a collision in the most traditional sense. And so my masses have to be equal. I don't have any release of energy. It's not requiring any energy up front. It's a billiard ball slamming into a bunch of other billiard balls. And when I have that, then if I calculate my Q value, it's going to be 0. And so this quantity is going to equal 1 when that occurs. So when I have the scattering interaction. Okay, so in order to set the stage, or not set the stage, so in order to conduct the rest of the lecture and look at the different reference frames, we're going to need to establish some nomenclature. We've already talked about a few of these. When I'm talking about the lab coordinate system, I'm going to use either a capital L or just drop that altogether. When I'm talking about the center of mass coordinate system, I'm going to use a capital C for that. Anytime I have a rest mass, that will be M subscript J, where J could be the two reactants, or either of the reactants, or it could be either of the products, just as we've done before. And if I'm talking about the lab velocity of my new frame of reference, or my center of mass frame of reference before the interaction, just like we talked about above, that's going to be VC. After that is going to be VC with a prime. And if I'm talking about velocity in the lab frame, this will just be VJ, where again we're going to cycle through each of those. So we could have Vx, V capital X, Vy, and V capital Y. And then when I'm talking about velocity in C, so this now is my velocity in the moving reference frame, in my new reference frame, in my center of mass reference frame. So the nomenclature for this will be Vj with a superscript C. And that's just going to be equal to the velocity in my lab reference frame minus the velocity of that reference frame. So this is what we used before the interaction. I don't know what that dot is there. VJC. VJC then will be equal to VJ minus VC prime after. Because again, the velocity of my reference frame before and after are not going to be the same. So that's the nomenclature, and by definition, I'm going to so that's my nomenclature. By definition of these last two velocities, the velocities in C, then I could write the following: Vxc that has to be equal to 0. That's before the interaction. And my Vy in that new frame of reference also has to be equal to 0. And these expressions that you're looking at here are collinear. That's what these expressions mean. They're collinear before and after the reaction. And the bottom line for what that means the end result here is that if I'm looking at my emission angles, either theta or phi in the center of mass coordinate system, then these are not going to be functions of either the masses or the energies. And that's part of the utility, or part of the value of what this center of mass reference frame provides. So to illustrate a little bit more, I'm including this figure from your textbook towards the end of this chapter, the end of chapter 2. There's a lot to unpack here, so let me kind of walk through this. You see an M capital X and M lowercase x, and so this is going to be my target. That's my capital X. This one is my projectile. And then I've got, on the reaction side, this is M capital Y, so this is my heavy product. And then this one over here is my light product. And you see this legend over here. So a solid line is going to be a trajectory that is occurring in my lab reference frame, and a dashed line is going to be the trajectory that I'm talking about in my center of mass reference frame. And so the x-axis, if you will, in this figure is different moments and different snapshots in time. And so I've got these two particles coming together. And so if I'm looking at this from the lab reference frame, or from the observer's point of view, and in this case I'm not even tying any frame of reference to any particle at all. I'm out here observing this, and I've got these two particles approaching each other. They collide and then have some nuclear reaction to have two new particles come out the other side. And so this vector here and this vector here are the approach vector, the fact that these two reactants are moving together. And if I look at it at a different moment in time, then these two particles are closer together, and then finally they get even closer, and at a point where then I have some reaction, some interaction. And then this is what trajectories I would be observing in the lab. I have my heavy product going one way, I have my light product going another way. And so I could then I could be an observer, just like we did up here, just like we illustrated up here. I could be an observer that's sitting somewhere between the projectile and the target. And then I could keep myself in that line and then move together in this new illustration that we're talking about. I would move at some velocity, and those two, if I'm looking at one way, I see the projectile coming towards me this side, and I look the other way, exact opposite way, and I see the target coming towards me. And I've chosen this velocity such that that net momentum is going to be 0. And so I can choose that velocity, and then I can choose this velocity over here, this VC prime, such that it looks as if the two particles coming on the other side of the reaction are also being ejected at opposite angles of each other. And so that's what you're seeing on this dashed line. And again, just to drive this point home, this velocity and this velocity are not the same. And because the velocities and the trajectories are not the same, these angles are not the same either. And so my angle here for the heavy product is theta. My angle for the light product would be phi, but I have corresponding angles in the center of mass reference frame. And that's theta c and phi sub c. And so if I'm in that frame of reference now, I'm moving at a different velocity, vc prime, and it looks as if the heavy particle's going this way, and I look exact opposite direction, and it looks like that light particle's going away from me in the opposite direction. And so these T1, T2, and T3, again, if you want to call this T minus 1, T minus 2, T minus 3 on the other side, these are different snapshots in time. So this is an illustration of what we're working with here. And so as you see the nomenclature that we're about to go over, you can kind of reference back to that figure and that table where we talked about different symbols and what they mean. But the goal here is to develop some ability or some relationships between the two frames of reference. And so I'm given data in the lab reference frame, and I can consider different emission angles in the center of mass reference frame. So that's another benefit of this, is that my emission angles are always going to be between 0 and pi in my center of mass reference frame. And so because of that, I can explore the different energies that I have as a function of that from 0 to pi, of that emission angle in the center of mass reference frame. So I want to simplify this, and here's where we're going to go back to the assumption that we had up until this lecture, and a reference that we go back to it. We're gonna take again that our target is stationary. So that's not exactly what we see here in this figure, because in this lab reference frame that we're depicting here, everything's moving. But in order to make the math easier, we're going to force that to be 0. And so because of that, if we go back to our expression for this VC, up here we assumed that we could still have some velocity, but if we get rid of this term, then this is going to simplify our analysis down here. And so we've got VC is just going to be equal to mx over the sum of the masses times Vx. And Vxc is going to be equal to Vx minus Vc. So let's put those expressions together. Actually, let's do this. So even though I have 0 kinetic energy and 0 velocity, as we said here, for my target, in the center of mass reference frame, it is as if it's moving, because I'm not tied to that target particle anymore. But in the lab reference frame, I take that to be 0. And so this then, it just becomes minus Vc, if you go back and look at the expression for my large particle. And so I've got Vx now in the center of mass reference frame. This will be Vx times 1 minus mx over mx plus m capital X. And then if I combine these together into a fraction, I'm going to see this is m over the sum of the masses times Vx. And so we, again, rather than talk about velocities, a lot of times, or almost exclusively, we're going to talk about energies. So So likewise for this V capital X in the lab reference frame, or in the center mass reference frame, this will just be mx over mx plus capital MX. So I'm expressing all of these in terms of the velocity of my projectile in the lab reference frame. I don't have the superscript c, and so by default I'm talking about what that velocity is in the lab reference frame. Okay, and the energies, again, we'll express this in terms of energies rather than just velocities. The energies here are going to be 1/2 mv squared. So in the center of mass reference frame, I need to express that velocity in that reference frame. And what I'm left with is 1/2 mx times m capital X over mx plus mx squared times vx squared. But this here, 1/2 mx times vx is v in the lab reference frame. That's none other than, if I combine these two, this is just my kinetic energy in the lab reference frame, so that's Ex. And so I can express my kinetic energy of the projectile in the center of mass reference frame as a function of the kinetic energy of the projectile in the lab reference frame. So this is just going to be related to the masses here. Squared times Ex. And so one thing to note here is that my Ex in the center of mass reference frame is always going to be less than or equal to whatever my kinetic energy is in the lab reference frame. So this is one equation that I want to make sure I'm comfortable with. Because I typically know the kinetic energy of the projectile. I know my masses, so I can easily just find the kinetic energy of the projectile in the center of mass reference frame. And I can do the same thing for my the kinetic energy of my target in the center of mass reference frame. And so that one will be 1/2 mvx in the center mass reference frame squared, and if I carry out that, then this is just going to be the product of the two masses divided by the sum squared, multiplied by that Ex. And so what do I have in this case? Again, I have that this is going to be less than or equal to Ex. So I start with that, and I can do the same thing in the product side. So I've got expressions now. If I know the masses and if I know the kinetic energy of the projectile in the lab reference frame, I can find both Ex and E capital X in my new reference frame, in my center mass reference frame. And I can do the same thing with the Y. And so rather than go through that whole derivation, here is the final expressions for both the light, the first one, and the heavy, the second one, particles in that on the product side of that reaction. So one thing to note here, these are four expressions that, again, all the input that I need is Ex, so the kinetic energy of my projectile in the lab reference frame, and I need my Q value. My Q value is right here. If you remember one of the most recent lectures where we were given Ex and we need to find both of these Ey, E capital Ey, or E capital Y, and we need to find phi. We need to find that emission angle, or that scatter angle. The very first step of that was to find my Q value. And once I did that, I could find all the other things. And so the process is more or less the same when I'm converting from a lab reference frame to the center mass reference frame. It's just that I have four now energies, and and additional angles to convert to. But one thing I wanted to highlight here is that if I look at this EX, in either case here, if I were to allow that EX to equal the following, then what I would be left with is a 0 inside here. And so my kinetic energy of both the heavy and the light product are going to be equal to 0 if this were to be the case. Then EYC equals E capital YC equals 0. So let's compare that, or we can just rearrange the terms a little bit. For this scenario, then EX is going to be minus Q times 1 over, combining these fractions together, I've got my plus my minus mx over my plus my equals minus Q times my plus my divided by my plus my. And if you recall from our last lecture, this is what we called the threshold energy. And so we didn't dictate that, and we didn't go through the derivation here, and so you didn't see this firsthand necessarily, but we didn't use that to develop these expressions at all. But it's if nothing else, it's comforting to see that it automatically just drops out of that, that we find and identify this threshold energy. Okay, and then the last expressions for EY, if you recall, in previous lectures we expressed our kinetic energy of the light product of our reaction as a function of the emission angle, that phi. Well, we talked a little bit ago about the fact that phi can go from 0 to pi in the center of mass reference frame. So because of that, it makes the analysis a little bit easier. And so a lot of times we're going to consider scenarios where we know the target, not the target, we know the projectile kinetic energies, and then we know the emission angle is going to go from 0 to pi in the lab or the center of mass reference frame. And so this expression that you see here is what takes me to find EY because I'm not given that in the lab reference frame, but I'm going to need that in order to eventually calculate to correlate my emission angle in the lab versus the center of mass reference frame. And so this is the expression I'm going to use for EY, and it's worth noting that EY is a max when that emission angle in the center of mass reference frame is 0, or 0. So that's what we call forward emission, and it's going to be a minimum when that phi equals pi, and that's going to be a backwards emission. And the last step is to relate our lab angles to our center of mass angles. And to relate those angles, we're going to use the following expression, which we're not going to go through the full derivation of this, but this is a simple geometric derivation, but looking at this figure back here. And the expression is we've got the lab angle on one side, and this is now the ratio of my energy of the light product in the center of mass reference frame and the light product kinetic energy in the lab reference frame, 1 minus the cosine squared of phi. This is phi c, sorry. So this here is going to be the scattering angle or the emission angle in my center of mass reference frame. So typically I'm going to know that, or I'm going to consider something, some range of that from 0 to 90 degrees or 0 to 180 degrees. I'm going to know something about EX. And so because I know the masses and I know EX, I can calculate because I know the masses, I can calculate the Q value. And because I know the masses and EX, I can calculate EX in the center of mass reference frame. I can calculate E capital X in the center of mass reference frame. I can calculate EY in the center of mass reference frame, and then I can calculate E capital Y in the center of mass reference frame. And so I've got those 4 energies just from knowledge of EX and Q and masses. And then I can find my kinetic energy of the light product in the lab reference frame from this expression, which I am going to use right here in this expression to ultimately relate this value of, or this range that I'm considering from 0 to pi or 0 to 90 degrees or something. I can relate it to my actual emission angle that the observer would see, that the lab reference frame would see. And so these are my 4 or 5 expressions that I need to have coded up. So we're going to go through the example here, 6.2, where we're demonstrating that. But just like any other calculator that I'm encouraging you to develop, you can create a calculator for this, where you just need to be given phi c, so the scattering angle, the emission angle in the center of mass reference frame. You're given phi c, you're given EX, and you're given the reaction. So the number of neutrons and protons, or the number of protons and total number of nucleons of both reactants and both products. I send those inputs into my calculator, and out comes the corresponding values of my EX, E capital X in my center of mass reference frame, EY, E capital EY in my center of mass reference frame, EY in my lab reference frame, and phi in my lab reference frame. Okay, so let's go to the final example in this lecture. We are starting with the neutron detection reaction that's listed here. I've got helium-3 as my target. I've got a neutron that is my projectile, and the result of this nuclear reaction is hydrogen-3, so that's tritium, and a proton on the product side. And I want to look at these ranges here. Range from 2 keV to 2 MeV, so that's 3 orders of magnitude range here in EX. This is the should say projectile kinetic energy. So I'm going to consider that, and then I want to determine the lab and center of momentum energies for X, Y, and capital Y. Well, the lab kinetic energy of capital X, that's an easy one. That's going to be 0. That's what we started with. That's what we chose our lab frame of reference to be. And then I also want to find the lab emission angles for these 4 different values of phi c, so the emission angle in the center of mass reference frame. And I eventually want to compare both the 2 reference frame. I want to compare the values for all 4 of these, all 5 of these. So I want to have 5 figures, and I've got 4 values for phi c, and so each figure should have 4 curves tied to it. And that's what I'll have the lab values on the x-axis. So going to and making use of, in this case, MATLAB But again, this is not going to be very different at all from any other code that you are more comfortable with, and really you should be using whatever code you are most comfortable with in this case. But you should be building these calculators along the way. So in this case, I've got my proton and nucleon numbers for my reactants. So on the one side, I've got helium-3. So helium has 2 neutrons, and it's helium-3, so I have a total of 3 nucleons. That's my capital X. My lowercase x, it's a neutron coming in. That's my projectile. It's a neutron, so I don't have any protons, and I have 1 nucleon. And on the other side of the reaction, I've got tritium, and so that's going to have 1 proton and 3 nucleons. That's my heavy product, and my light product is just going to be a proton. 1 proton and 1 total nucleon. And so I use my calculator that I already have, get my masses, and I can get all this from the nuclide table, and we've done that in the past, but I'm going to just use my calculator that I've already built. And so I'm also going to use my Q-value calculator. This is really not much, and I'm happy to reveal the script here. All I'm doing is adding the masses from the reactant side, subtracting the masses from the product side, multiplying by 931.5 to convert from AMU to MeV. And so that's my Q value. In this case, the problem didn't ask me to find these other barriers. I know I'm not going to need to look at the Coulomb barrier because I have a neutron as my projectile, so I'm not going to have to worry about that. Unless I have some intuition to this problem, I don't know if the Q value is going to be positive or negative, and so maybe I'll just calculate this just in case. And then I'm going to look at 4 different values of this phi c, and in this case I'm going to create an evenly spaced vector in the log space, and so the inputs to this function are the exponents that I'm taking the value of 10 to. And so I'm going from 2 keV to 2 MeV, and so in terms of MeV, that's 2e to the minus 3 MeV up to 2e to the 0 MeV. And so this creates 15 data points within that range of 2 keV to 2 MeV. And you're welcome to do this any way you want, but the point is create yourself a vector to consider for the EX, just like it mentions in the problem statement. And this is just allocating space in my memory for this. This is definitely not necessary for the size of matrices that we're encountering here. But then I'm just going to loop through this. And so I'll use the expression for, these are the ones that we had put boxes around in the notes. I've got my projectile kinetic energy in the center of mass reference frame. I've got, and that's a function of my EX. I've got my target kinetic energy, which is also a function of EX. And you notice that the only thing in front of here is a constant. I mean, these masses are not changing. I have mass of X and mass of capital X. And it's the same story with this one. And so these aren't going to be dependent on phi at all. And we'll plot these and prove to ourselves that's the case, but we're not expecting to have any phi dependence at all. And then we're going to do my light product, my heavy product on the product side, and the expression that we had in the notes for both of those, and then the expression we have in the notes for EY, which is the kinetic energy of the light product in the lab reference frame, the expression that we provided in the notes there. And once I have that in the lab reference frame, I'm going to use the standard way of calculating that we've always used to calculate the energy of the heavy product in the lab reference frame. And so I've got these, I got CC here. I'm not going to bother calculating EX, capital X, because I know that's 0. And then I'm going to use that expression for the phi, which is the emission angle in the lab reference frame, as a function of this emission angle in my center of mass reference frame, which is what I'm starting with. So And so I just loop through each of those and I create myself some matrices for all of these parameters, and I then plot the results. And so figure 1 is going to be EX versus EX in the center of mass reference frame. Figure 2 is going to be the same thing for capital X. Figure 3 is going to be the same thing for Y, and then for capital Y for figure 4. And then figure 5, I'm going to compare the angles. So the angle in the lab versus the angle in the center mass reference frame. So if I run this, I'm going to get 5 figures popping up here. So let's look at these one by one. The very first figure is my energy of the projectile. And so as I go from 0 to 2 MeV, I'm always seeing something less than, as I knew it would be, something less than in my center of mass reference frame. And so I've got my 4 angles that I'm considering as part of the problem statement, but again, it's not dependent on those angles at all. I could put anything in there, it's not going to be a function of angle at all. And I see the same thing for E capital X, and this is one we probably didn't need to plot at all because we know that it's 0 in the lab reference frame, and so every data point here is 0, but again, it's not dependent on the angle. But now as we get into Y, here's our product side. We have in the lab reference frame versus the values in the center of mass reference frame. And if you go back to the code here, we didn't expect this to be a function of angle either. So the question is, why are we seeing different curves? And in the first two, they were just lying on top of each other. Every curve was exactly identical to every other curve. But in this case, we don't see that because if we were plotting this versus EX, then we would see, again, all those curves lie on top of each other. But we're plotting EY versus EYC. So EY is dependent on this angle. And so as I go and I look at this figure again, I can see that for any value of EY, let's say, each one of these data points has the exact same Y value. So each one of these data points represents a different angle in the center of mass reference frame. And so I'm still seeing that the value of EY in my center of mass reference frame is not dependent on the angle at all. But EY in my lab reference frame is indeed dependent. And so that's why I'm seeing 4 different curves here. As I go to my capital Y, again, I'm seeing 4 different curves there. It's interesting to look at these two side by side, actually. So we'll start with figure 4 here, which is with my heavy product. And as I look at my emission angle, I start at 0 degrees and I go to 30, then to 60, then to 90. It's maybe hard to see here, but if I insert a line from 0.2 value up to 0.6 and then 0.6, so that is a line of constant slope, and that slope is equal to 1. So if my data points were on that line, that means that EY in my lab reference frame would be equal to EY in my center of mass reference frame. And you see that as each one of these data points represents on any one curve represents a smaller and smaller value of EX. And so as EX goes down, I'm starting to get to a condition where EX is small enough, then my two EYs are going to be equal to each other. But interestingly, I start at 0 and I go towards 90, and so the data you're seeing here, I'm transitioning across this line. So for anything with a center of mass emission angle from 0 to, in this case, 60, and a little bit more than 60, we would see things on the top side, on the left side of this line, meaning that my energy, my kinetic energy of the heavy particle on the product side is actually bigger, a larger value in the center of mass reference frame than it is in the lab reference frame. But then there's some angle at which when I cross that angle, I get the opposite scenario, where my kinetic energy of that heavy particle in the center of mass reference frame is actually smaller than the same value in the lab reference frame. And so if we look at these same EYs, or the same behavior for my light particle, let's go ahead and draw another line here. Let's start at 0.5 and 0.5, and let's go up to 1.5 and 1.5, which is going to be right there. So you see in the light particle scenario that even up to 90 degrees, I'm not crossing that at all. Now we'll play around with these numbers here in a minute to show you that there is an angle here where this also crosses over that 1-to-1, x equals 1, y equals x type behavior. And you could glean that from the expression for EY, and you can look at the emission angles. You can see where EY is going to equal EYC. So now as I look at the final figure, I look at my emission angles. In this case, it's a little misleading what's being plotted here. These lines shouldn't be connected to these data points. They should just be horizontal lines, because each of these data points in a cluster here represent my different values for EX, my projectile kinetic energy, and each of these 4 points represents, in this case, what I'm dictating is what's on the y-axis here, and so this is a little bit misleading of a plot, but so for any fixed value of my emission angle in the center of mass reference frame, I can get a range of actual emission angles in the lab reference frame as a function of that projectile kinetic energy. So we can say we're going to explore this a little bit. So let's change this from 90 to 110 or so. And let's look especially at those EYs. So let's go and draw another line here from 0.5 up to 1.5, 1.5. So you can see that I've crossed the, oh, my label is off. This should be 110, right? It should be 110. So somewhere between 90 and 110, I actually crossed over this line again. Or not again, but as I expected I would, right? It's not that if I go to pi, then I somehow converge so that EYC is equal to EY. And same story over here. Well, this one had already crossed over, so we don't need to discuss that any further. But there's going to be an angle for, and it's going to be a different angle for E capital Y compared to what the angle would be for E lowercase y. The energy of my light and heavy products of the reaction, but there is going to be an angle where that crosses over from this one being larger than that one to the exact opposite. So you would be well served to recognize the fact that I could take this, rather than calculate this in a loop, I could create a function that simply takes inputs of my masses and my kinetic energy of the projectile, which again is what we typically start with, and then a range of phi in the center of mass, or just one value for phi, and then outputs all these lines here, the things that I would want from that analysis. And so then you can just loop through it as many times as you want. In fact, I could reproduce this in a different way and get the same results by creating a function that does everything that's going on in here and giving me 1, 2, 3, 4, 5, 6, 7 outputs, and my inputs would be my 4 masses and my EX and then my phi. There's Q in here too, but I could either make that another input, or I could just do a quick line of calculation in that same function. Okay, well, that concludes this lecture, and we will see you again for lecture 7.